This is the total angular momentum. We define the total angular momentum of a spin 1/2 particle by the relationship here, meaning that the components add. For example, Jz is the total angular momentum, which is Lz plus Sz. The quantum mechanic operators representing components of J also add. So we have for X here, Y here, and Z here. So they're all the same. The operators are each the sum of differential operators, such as L hat of X, that act on the function of theta and phi, and a 2 times 2 matrix, such as S of X, that acts on the spinors. For a spin 1/2 particle, the spin up and spin down spin up and spin down relative to the z-axis are given here, where up is 1 0 and down is 0 1, and we can construct state vectors that are products of the spherical harmonics and spin vectors, which are given here. These are the spherical harmonics, Y L sub m, which should be familiar by now, and these are them with the spin states up and down. And when an operator such as Lz acts on such a product, if it operates as usual on the spherical harmonic and ignores the spinor, and a spin operator ignores the spherical harmonic and acts upon the spin operator. Now, given that S of Z spin up equals plus 1/2 h bar spin up, and S of Z down equals minus 1/2 h bar down, and L's of Z acting on the spherical harmonic here is mh bar and the spherical harmonic. And what would be the result of operating on here? Now the answer is here. It's just basically plugging this in and simplifying, and so using the eigenvalue equations given, we end up with this here. And now the operators obey commutation relations similar to orbital angular momentum or spin. So J of X, J of Y equals I H bar J of Z, and you can see so on and so on. And J squared equals JX squared plus JY squared plus JZ squared, which commutes with all components of J hat here. Now, to summarize, for a spin 1/2 particle in a spherical symmetric potential energy well, VR, when the spin-orbit interaction is neglected, the Hamiltonian operator H commutes with L squared, Lz, S squared, and Sc. When the spin-orbit interaction is included, the Hamiltonian operator H SO, which is the Hamiltonian for spin-orbit interaction, commutes with L squared and S squared, but not with Lz or Sc. Instead, it commutes with the total orbital momentum, angular momentum, and J sub Z. For any spin 1/2 particle, S squared equals 1/2 plus 1 h bar squared, which here, 3 h bar squared over 4, no matter what state the particle is in. So this operator does not help specify the state. However, eigenvalues of J squared and Jz do help us specify states, and we need to know the possible eigenvalues of the operators. Now, the eigenvalues of J squared are similar as before when we had L. We had the operator L. J plus 1 multiplied by h bar squared. where J is the total angular momentum quantum number. The quantum number is always non-negative for spin 1/2 particles, with L not equal to 0. If it has two possible values, J equals L plus 1/2 and J equals L minus 1/2. For L equals 0, it only has the value J equals 1/2, and the eigenvalues of JZ and MJ of H, where MJ is the total magnetic quantum number. This can have values of MJ equals -J plus 1, comma, ... J minus 1, comma, J. So there are two J plus 1 different values of MJ for each J. Now, because the Hamiltonian H at SO for spin orbit interaction and LZ don't commute, we can label exact energy eigenvalues with L and M, but H, the Hamiltonian of spin orbit interaction, L squared and J squared and JZ do commute, so we can label each eigenvalue L, J, MJ. The fact that L this is angled brackets in direct notation. L, J, MJ is a simultaneous eigenvector of L squared, J squared and JZ, is then expressed as given here. We expressed these earlier on further up, but this is my indirect notation now, taking into account the other components as just explained. The specific combination of spherical harmonics and spinors that have these eigenvalues are of the form here, where y else of m, as we know, is a spherical harmonic, is a function of theta and phi, and a, b are just constants. The harmonics occupy these terms both have some value of L. This means that Lj, Mj is an eigenvector of L squared, the total angular momentum operator. However, the spherical harmonic with the spin-up state, given in Dirac notation here with the arrow, has a lower value of M than that with the spin down state. This means that Lj, Mj is not an eigenvector of Lz, but is instead an eigenvector of Jz. Now Jz operating on here on our eigenvector gives this here, the momentum operator acting on Z and Sz, and we have here with our constants, we're plugging into before the equation before with our constants, and so we end up with this, with Mj H bar, which is similar to our azimuthal and without spin. To ensure that Ljmj is also an eigenvector of J squared, the numerical coefficients a and b must be chosen carefully. For example, if L equals 1 and J equals 1/2 and Mj equals 1/2, we get this here. And we could verify this is an eigenvector of J squared by writing spherical harmonics out in full and using explicit terms for orbital and spin angular momentum operators that operate on in J squared. Here's a few eigenvectors of L squared, J squared and Jz for L equals 2, L equals 1. Right, and that's it for this little micro lecture, but please do subscribe. I'm going to get better at this, I promise. Thank you.